I'm Bill Nitzberg. I'm the CTO for the PBS Works division at Altair. I'm doing a little bit of a different kind of talk than I normally give. I'm normally focused on real sysadministrator techie kind of things and how you build stuff. And after talking to the folks at Intel, I really wanted to actually tune this talk, and this may actually, you guys can all get up and leave once you hear this. I really wanted to tune this talk more towards sort of application developers, and maybe a little bit more towards application developers who maybe are sort of a little bit newer to HPC, and maybe you've built something great on, say, a Windows box, and you want to connect it up and you want to get a little more resources. So hopefully there's a little bit for everybody, but just so you know, I have tuned the talk in that direction. So when you're here and you go, well, why isn't he talking about that? Why didn't he talk about the details of his product? Oh, and also, I'm trying not to be commercial, although I can't help myself to tell you a little bit about Altair, so I'll do that too. So for those of you who want to do email, basically, you can deliver a better user experience. You can do things faster and make things bigger and do more runs by converting sort of your HPC application from, hey, just run on the desktop, to, okay, run some stuff elsewhere, and take advantage of clusters, supercomputers, clouds. And all you have to do is separate out sort of the solver component, kind of stick it up somewhere else, and then connect together with a little scripting sort of with a workload manager. Okay, so that's all I'm going to say for the rest of the whole thing, and the rest is sort of building on this, and I do this because I know that people, when they first come to a talk and they first hear you saying that people are interested and you haven't opened your computers yet, and so you're like paying attention, so you now can leave. Or actually go back to what you're doing. Let me step back though. Okay, anyway, that was the summary of the whole talk. Now I'll wander you through a couple of different spaces. So one is, Altair believes that HPC really improves people's lives. Actually, this is really cool. I put this slide together and this sort of message together prior to last year's supercomputing, which I loved last year's supercomputing sort of hashtag, which was HPC Matters. And I'm actually kind of disappointed that they changed the hashtag to HPC Transforms, because I think HPC Matters is way more important. But I think HPC actually improves people's lives, and that's why I'm doing this. That's why I get excited about what we're doing, even when it's some weird low-level, device drivery thing that nobody in their right mind could care about except for me and the 6 other people in the world who really need it. But if you've ever been outside, for example, or driven in a car, or flown in an airplane, or checked the weather, or dropped your cell phone, or the reason that the airplane used a little less fuel, the airbag deployed correctly if it wasn't Tata, and the child safety restraints worked in your car, and your cell phone didn't break when it landed on the ground, that's all HPC. The reason that when you go and you get a full body MRI or something, and we can map out all the little veins, and then we can figure out that there's a little pinch somewhere, and design a perfect stent just to actually open up some artery inside your heart. That's all HPC. So it really actually does improve people's lives. Okay, two marketing slides, I think, only for Altair. So Altair, here's I think we bring a pretty unique perspective to high-performance computing. Altair's been around for, I was going to say 25, but 30 years. Global offices all over the world, about 2,000 employees plus. But actually, what makes Altair really unique, and what I think makes us really kind of know HPC, is we don't just do what I'm going to talk about, which is workload management. With PBS Professional. We actually have a large development team who builds applications for high-performance computing. So we build structural optimization applications, Radios, OptiStruct, computational fluid dynamics, electromagnetics. And so we really actually have an entire team who then depends on my team to help them get more access to computing power. But in addition to that, and this is what makes us unique, is there's 700 plus consultants in the company who actually go sort of on-site for companies or do consulting work for companies who take our products and take the rest of our technology and do things like, reduce wing spar weight for an A380, right, using all this stuff. And then they, have problems with both the HPC apps and with my workload management stuff, and they come back to us and we go, well, what do you mean you're having a problem? No, it's perfect software. No, it's not. You need to fix this. And so there's this great feedback loop. And so it actually also makes it a really fun place to work. Where I sit I said a little about this. There's actually a couple other things that Altair does, but I sit actually in the PBS Works division within Altair. And you can see Altair is actually pretty broad spectrum of things that we do, including, I think if you go to Home Depot, you can see some of the products that actually came out of Altair there, which is a solid state lighting division. Okay, so part one, marketing. Part two, I don't know how many parts. This is going to get me in trouble when I'm saying part two. Part two, why? Why am I talking about job launch or using high performance computing? And why do I want to tell application developers that it's time to get off the workstation and try to actually use some more resources? Or what's the motivation behind this? Okay, so I put together a blog post over the summer, and I was trying to think back. By the way, I could use all 50 minutes on this, so I'm not going to try to do that. I was trying to think back over. Someone asked me to look into the future, and I thought, well, that's really hard. Let me look into the past. That's a little bit easier. And I put together a blog post sort of looking backward over time at some various trends and things that I was thinking about in supercomputing. And I'm just going to highlight two of them here. And if there's time at the end of this, I'm happy to go back to this and just have a conversation about other stuff. This is also actually, if you look at my name and you search for some unique word in here, you'll probably find the blog post if you want to actually get this slide. Two trends that were actually really interesting, I thought, were that the system sizes are getting bigger, the stuff that people have access to, right? In the 80s, tens of cores was actually a pretty big system. One core was a pretty big system in the 80s. Things are really big now. So there's just plain more computing power available, right? So if you're still writing an application for the desktop, look, there's okay, yeah, sure, your desktop has 20 cores, but there's millions of cores out there really readily available. And the second interesting thing is the number of users who not only sort of are available, but who are taking advantage of what sort of we would consider high-performance computing has exploded. But in a different way. It's exploded in that there's tons and tons more users, and the nice way of putting it is they're novices to this space, right? These folks are used to using, these folks are used to using GUIs and phones. They're not used to typing, MPI run -np whatever and missing some semicolon somewhere and going, it's not working. I'm going to go back to using my phone and do something else. So both of those things actually create this really big opportunity to take your application and to scale it up. So to just do more with what you have, and also to take your application and to reach into more places. So there's if I talk, I can still use this slide. If you think about sort of what's happening here, these systems on the right-hand side are huge, and a lot of my time I spend in my day job working on how to make these huge systems work really well. But the vast majority of the people, I think, who are taking advantage of HPC now, and actually moving forward, certainly even more moving forward, are going to be these small and medium enterprises. The folks who haven't really had access before. And anything that we do to sort of improve access to high-performance computing, to the tools and the outputs, is going to explode. And we're going to go from tens of experts to really tens of thousands of stuff, which is going to make my car and my cell phone even better. So it's going to help me. So that's what you should be thinking about. So how do I think about this? Well, I think about sort of these systems, the not workstations, so the clusters, the clouds, the supercomputers, as being used sort of from two dimensions. So from end users, and I don't know how many people are end users here, but if you're an end user, what you want and what you're used to, because you're working on your workstation, is you want instant access and no limits. Of course. I mean, everybody wants, this is not my phrase, but I'll repeat it. I wish I could remember who it was from. Everybody wants disabled parking. Who wouldn't? You don't want to have to deal with failures, and you want to use the user interface that you're used to. You don't want to learn how to do something that's complicated. On the system manager side, they're like, hey, these are expensive systems. I need to manage shared access, and I need to manage costs. And okay, they're big. They're made of commodity parts. In order to make them affordable, I plugged those commodity parts together with commodity networks. And although it's as good as it can get, once you have thousands or tens of thousands of parts fail. So I need some strategy for dealing with these failures. That, of course, doesn't actually reflect back to the users. And I need to see what's going on. I don't want this, I don't want to look at one system. I need to see everything, right? And what marries these things together is a workload manager, right? So it plays, and effectively, in my mind, one way of talking about a workload manager is I'm going to put myself on this side for now, and I'm going to pretend that you guys are on the end user side. Just bear with me. I don't know. Some of you are probably system administrators. I think of the workload manager's job as protecting people like you from people like me. Okay. Part 2. You have an application. Nope, this is part 3, right? Part 3, thank you. Part 3. You have an application. Your application is running on some desktop. Okay? Pretty standard, no problem. Probably some inputs. Processes them into some outputs. That's super standard. The vast majority, I'm going to make this claim. I actually don't have any data to back it up, so don't ask me the data. That the vast majority of things that we are going to take advantage of in HPC in the future are things that are just like this on people's desktops. They're not running. They're on workstations. They're not running in high performance computing centers, and they're limited. They're limited because they're limited to the workstation performance, what's running. They're limited to whatever is on the workstation memory. Okay, fine, workstation memory is getting bigger, but it's still workstation memory. You want to run a 1,000-way parameter study, for example. That's going to be a little hard in your workstation memory. So limited parallelism. They're limited in technology. You want to put a Knights Landing system out there. Not everybody's going to stick one of those in their workstation. Hopefully, Intel wants us all to put one in our workstation, but maybe some people won't have them. Limited resilience. That machine goes down. Well, everything that you're gone, right? You can't pick up your phone and connect to your workstation. And there's all of that put together. Sort of gives you a limited user experience. Or put another way, if you actually try to run HPC on that machine the same time you're doing some GUI thing, you're going to get a limited user experience. So what we want to do is we want to, obviously take that application, break it apart, scale it up, speed it up, give you access to the new technology, and make the experience better. Okay, so we have it. Right now, the application's sitting, running on your desktop. Really simple. Part of that, I don't know if you could see here. This is my graphic artist. She had to actually show me this. I didn't know this, but part of that application is somewhere in there is the solver part. Okay, so take the solver part out. And what we want to do is we want to move the solver as a separate component off the desktop, package it up a little bit, and stick it on our cluster or stick it on our supercomputer. It turns out, and I was actually surprised to find this because I work in this space, and I always think that every single HPC application already does this and already has a batch mode, but it is not true. That there are huge quantities of applications, and this is in the space where small and medium folks live, where the application itself is this GUI application. The only way you can get it to do its thing is if you pop the GUI open and you actually interact with it. So the first thing that we need is we need people like you, again, as application developers, those of you who are application developers, to start thinking about how do I take out the solver portion of my application and make it into some batch thing. So a batch thing is something where I can just say, run it on a command line, it takes some inputs, it produces some outputs. By the way, I'm using a picture of a computer, but it could equally be a cloud, that's fine, right? So a cluster could equally be a cloud, it's no problem. And then, instead of taking the input file and just passing it to the desktop, what you need to do for workload management is 4 things. So 1, you need to put a little package around the input file. Okay? Then instead of pushing the load button, you need to submit your input file to the workload manager, which will eventually get its way onto your cluster. At that point, at some point later, we'll talk about that in a second. At some point later, the actual solver itself will run. Compute what you need. By the way, if you wanted to do a 1,000-way parameter study, instead of submitting 1, you can submit 1,000. So you're not limited to what you want to do. And it'll take, if you're submitting off to, say, Amazon, and you've provisioned yourself 1,000 machines, which we can do as workload manager purveyors, you could get done 1,000 times the work in the time it would take you to do one thing. So really cool. While it's running, you can actually connect your application. You can find out what's going on. You can read input files. You can read intermediate results. You can get details of what's happening. And at the end, you'll just pull back your output file. And so that's it. There's four things, and those 4 things are, in fact, your interface to the workload management system. So package your work, submit, monitor, and get the output. So that was number 3. Let's dive in a little bit. So what does that look like in practice? So in practice, it's pretty simple. So I'm now going to switch to use examples from what I know best, which is PBS Pro. And I apologize for that if you're used to a different workload manager, but that's what I know, so I'm going to use those examples. Mostly they translate. I mean, of course, PBS is better than everything else, but look who's talking. So simple stuff, really easy. All you'd be doing for packaging your application, say you have you've created this thing called MySolver, is you would just say, hey, my thing used to run on my workstation. Maybe we used a couple of cores, so we'll say, and it used a little bit of memory. So you just would tell the package that you would give it would basically be, here's the resources I need, which minimally is kind of like how many CPUs and how much CPU is memory, and then pass the input file along. And that's it. And then submit it separately. Equivalent kind of easy commands if you want to actually do the monitoring. So qstat is just a way of monitoring. Qalter will change. Qdel will delete the job. And then at the end, you just get your output file. And I'll say one thing at the very end about how you get your output file and the input file. So the thing that's different about a workstation than about an HPC system that's sort of on-premise or off-premise, but not on your workstation, is this whole idea of queuing. I'm not going to say queue because queue is a convenient abstraction. But what it implies is that you may not run right away. If you were to run right away, which is what would happen if you wanted to run your 1,000-way parameter study on your workstation, is you'd actually probably cause some interesting traffic jam and you'd have to reboot your workstation and start over. So a queue is the nice abstraction that you use, that workload managers use, to sort of say, we can't do everything at the same time. We have to, and by not doing everything at the same time, we can actually streamline access, make sure that the most important things get done first, the second most important things get done second, but most importantly, from an application writer point of view, the most important thing we can do is we can make sure that multiple things don't overload the system. But it's not just that. So, okay, is this part 3, part 4? 4. Okay, part 4. So why workload management? So why workload management actually is now here's where as a user who wants instant access, no limits, natural interface, and no failures, you actually don't care about a workload manager. It's nice that workload management can deliver that for you, but that's not you wouldn't go buy one. So really, who buys workload management and the real value delivered in workload management is taking a shared resource and splitting it between 2 really divergent goals. The first goal is, hey, I have an enterprise policy. I'm doing this I bought this very expensive resource and I want it to be used the best way it can be used, which means I have a whole bunch of different things going on in my enterprise. Imagine I'm some large Fortune 100 company, and I'm building a new object, say an airplane, and there's some part that's broken on that airplane, and now on the factory floor that's pushing that airplane forward, it's stopped. Okay, the cost for that factory floor being not moving, probably probably tens of thousands of dollars an hour, right? So I need some part sort of adjusted. Great thing these days, of course, is I could 3D print a new part if I really needed a new part. So once I get the new design, I'm probably okay. But I've realized that this part's not working and I need a new part. I need to go design it. So I hand it off to some designers. They run, they run some simulation, hopefully with Altair software, and it comes out with the new part. Okay, so thinking about how I want to use this system and thinking about goal number 1, if I'm the owner of that system, do I care about utilization for those few hours that my factory floor is not moving? And no, I do not. I'm losing whatever, $10,000, $50,000 an hour. If the only thing you do is support those engineers in order to get that part back to the factory floor, that's really important. So that's why the #1 goal is to really run the right job. So now in the public sector, more in academia, really the right job ends up being try to be fair to everybody so the system administrator doesn't get any phone calls. In the private sector, it's really try to be fair to the most important person because nobody else matters. Or in proportion to how they matter. So then once you do that though, once I'm actually building this part, once all of the simulations for the part are actually in the system and they're going through and there's leftover space, great. Then goal #2. Now, make sure those are running as fast as possible, put them in the right places, but also make sure nothing else is wasted. So if you have holes in the system, fill those in. If there's machines that you have holes on that you have no work for, turn them off. If there's software licenses that are unused, figure out if there's something that somebody might be wanting to do that isn't very important but would use that software license, because it's wasting money if you have a software license you're not being used. So that's goal #2. So goal #1, policy. Goal #2, use it. Sort of behind the curtain a little bit, what the workload manager is doing after that queue is, so you're submitting a job, it's sitting in the queue. Maybe you want to monitor it. Eventually, that job is actually going to get scheduled. So mostly, I end up talking about the scheduling part all the time, and I'll say a few things about that. Once the right job has been chosen and the right place to run the job has been chosen, you'll want to do some kind of provisioning. Provisioning could be as simple as just simply starting up, doing a fork on a node and then running your solver. It could be as complicated as connecting to Amazon and firing up 100 machines, waiting for them to come up, building a VPN, doing all this other stuff, and then launching your job. You'll want to execute the job. Again, you'll want to keep monitoring it. And then finally, at the end, one of the great things that you get with workload management software from the administrator's perspective is you get all this accounting data about who did what when. Could you have done it better? How much energy was used, for example? All that sort of stuff. So that's great. I'm going to skip one slide here, so let me see if I can do that. So, okay, under the covers, what kind of things are happening? Again, from just the systems viewpoint, cool things we do as workload management vendors in scheduling, backfill scheduling. So if you, and this needs a little tiny bit of explanation. So on the left-hand side, your system is full of running jobs and they're going to end, and so the time now is the very left-hand side. And we're looking at a picture of time across the bottom, and the space, meaning which nodes are being used, is filled up on the horizontal axis. And so here's what the system looks like now. It's like there's a bunch of running jobs. The most important job, which is job 1, is going to run next, and it's going to run whatever in 2 hours or something. And then job 2 is the next most important, and it'll run after job 1 starts because it needs all those resources it can't fit. And then job 3, 4, 5. So what backfilling does is says, well, that's great, but rather than just wait and leave these holes around, let's go ahead and see if things fit, and we can move them forward in time. We can get a little bit more done a little bit sooner. Plus, we can get actually a little more utilization. So that's what backfill scheduling is supposed to do. There is an alternative to this same thing, which workload managers can also do, which is just turn those things off. They're not being used. Maybe it's in the middle of the day in Maui, and actually having your system 100% used, not such a good idea in the middle of the day. Maybe at night it's okay, but in the middle of the day you'd rather save the power because the power is more expensive than the system. In that case, you can actually just turn those systems off, or if you're in fact using a cloud, maybe you just unprovision them. And turn them off. So you get choice. But backfill scheduling is, if power is not a problem, it's one of the ways you can boost utilization, and you can actually speed stuff up. One other reason why you want this whole workload management stuff is some topology aware scheduling. And basically, the systems, once they get larger, get connected by networks, right? And I didn't draw a network. Well, okay, I draw little network diagrams for you. Then those networks, come in a lot of different flavors, hierarchical and weird hypercubes and meshes and the dragonflies and all this other stuff. What they all have in common, however, is some of the nodes tend to be really well connected, And as you sort of get larger, you can get further apart and you can end up going more and more hops. And if you take an application that's, say, going to run on 100 nodes, you kind of want it to run on a whole bunch of nodes that are really well connected for two reasons. One is you minimize latency because you minimize the number of hops just for that application. And the second one is if you've put all of those bits of the application together, you've minimized the contention with other applications, right? Because if you have imagine two applications trying to, or anything trying to use the same road, there's going to be a certain amount of contention. You're going to have to wait for things. So that's the extent that you can sort of push stuff together is the extent that you can speed it up and remove latency. And so that's another thing we do inside of workload management is we actually do this packing. This is actually what helps run jobs as fast as possible. And this is an example actually of someone reporting back. I got their permission to use it, but not by name. An example of someone who actually implemented, they had a whole series of runs, and they were sort of analyzing what was going on, and they were like, hey, sometimes these things take a little longer than others. And this was just an example of 3 runs, exact same application, exact same input file, and it just took longer, and it just depended on where it ended up on the system. So sometimes it was spread out, sometimes other things were running, so sometimes it ran faster, sometimes it ran slower. We implemented some topology aware scheduling with them, and they got not just, actually the amazing thing, I expect consistent results, that's good, but the amazing thing is consistent, and in fact, it was always faster, so they were really happy. And I said a little bit about this. The third thing that I think is actually super modern and really important in workload management that folks are doing is power management. And again, as a application developer, not really important to you. As a systems provider, probably really important. The amount of power that these systems are using is a huge proportion of the operational cost. A lot of times, once you bought the system, okay, you've spent that money, that's sunk cost. You don't have to spend that again. Yes, it's capital cost. If you were doing some analysis, over 5 years before you bought it, you might look at this. But after the fact, you may have paid that money already. So the only place that you have a lever to move up or down or to try to decide where you can save money is in operational costs, and power is a huge proportion of operational costs. So workload management systems let you measure, monitor, cap, and more importantly, report power usage. I think one of the things that we will see in the future, by the way, this is from a paper that was presented, I'm going to get this wrong, presented in 2012 by the DoD. Based on some analysis they did of turning machines off when they were not used. And this wasn't just sort of like, it's not used. This really was that picture that I had for backfilling, where there was just these little holes for a few hours here and a few hours there. And they took that data and they ran it and they estimated, okay, how much money would we save if we turned those machines off? And Mana is actually in Maui. And that's why I used Maui as my example, because electricity in Hawaii is really expensive. And so this is what their yearly savings if they just turned machines off. What I think, though, I was going to say was, in the future, or what we're going to use this for today, most often, is not the limiting factor, or not even turning it on and off, although I think that's really cool, and people will use it for that, but it's the accounting part. I don't think users are aware, I don't think I'm even aware of how much is it really costing when I run one of these applications. When I do a simulation and I decide, I feel like I should do a 100-way parameter study to figure out all the different ways, I'm going to drop this, and I want to figure out, all 1,000 ways that I might drop it in order to hit the cement, and I want to make sure it doesn't die. Okay, if it turns out that it's, $300 per run of power, when I go home, my children, okay, I don't have any children, but if I had them, my children would be asking me to turn the lights off and stuff in the house, right? Because I did that as a kid to save power, and if I'm already burning a megawatt of power at work, I'm going to feel bad, and I might actually spend a little bit more time thinking about, do I really need all 1,000? With 700, I cover the space really well. Maybe I should use a tool that helps me, define exactly how many runs I need, because I can save a bunch of power in addition to actually getting things done faster. So I personally think that the measurement side of this is just at its infancy, and that's going to be what's pushing us forward. On the HPC side, again. Tons more stuff that workload managers do. These are some examples from PBS. Examples all over the place, though, from anywhere else. Okay, let me take us back, and I've totally lost which section of my talk this is now. To expand 5. See, this is great. At least 2 people are listening. I didn't even think about making a quiz in here, but this is awesome. This is awesome. Okay, let me go back to the packaging. So if you package up something, I showed you what a really simple thing was. They do get more complicated. And since I did want to give you some idea of how to get started, by the way, if you want to get started, you can, of course, call me, call us, and we'll help you get started. But some idea of how to get started. So it does actually, simple stuff is simple, but you can also do more complicated stuff with some caveats. So one more complicated thing you might want to do is that very top line there, which is you might want to not run a simple SMP job. You might want to run some kind of MPI job. I think I only have 8 MPI tasks here. You might want to describe your whole job, in fact. And workload management, part of the packaging is you describe the resources you need for your job. So in resources, at the simplest form, are CPUs and memory, but they can be actually very complicated. So you can describe an arbitrary hybrid MPI, OpenMP application with different amounts of memory for different things. And the magic is the workload manager is going to go out and it's going to find the best place to run that, to run it as fast as possible, given the hardware that you happen to have available, given what's actually being used right now. So in this case, it's finding a really good spot, but maybe if there's only fat nodes, it will actually crunch some stuff together and put them on fat nodes. Maybe it would spread it out more, right? Depending on what the best thing is now. Not just for your hardware, but also for the workload, and not just for your hardware today, but the same description is going to work tomorrow too. So in this case, this is a 7-way MPI job, 64 gigabytes on rank 0. Each one's got 4 OpenMP threads, and each one wants 1 Xeon Phi. So you can also describe all sorts of other stuff that you might need. Temporary scratch space, software licenses, which are often needed, a time limit. Queues, I said, queues were mostly an abstraction, but actually that abstraction is used a lot by a lot of sites in order to define some site policies or give you information about what, when your job might run or what priority it might run at. You can do containers, you can, this is not a real MasterCard number. If it turns out this works, it was totally by accident. I actually had one that looked more real, and I purposely changed it to look really fake. But and I was thinking, what if somebody types that in and it works? That'll be bad. But you could do all sorts of accounting information. You can even do parameter studies, right from inside, and describe what you're doing. So that's it. It's really simple, but there's a couple of things that you should keep in mind. Okay, so, and I only have sort of 3 things to keep in mind when you're doing this as an application writer and you're trying to interface. The thing about workload management is, if you come and you talk to me or you talk to any workload management vendor, you will get a very clean story about exactly how things work. But the reality is, once this system is deployed at a site, there's a certain amount of configuration that happens. And it's in that configuration that actually makes it hard to build one application that runs anywhere. And I'll say a little more about that. But one place to start with is this notion of wall time. So actually, a lot of sites just have this wall time as optional, so maybe you don't need to worry about it. But some sites actually use wall time, so you might need to worry about it. The deal with wall time, though, is 2 things. One is it's often used for prioritization. So the more accurate you supply wall time, often, the sooner your job will run. So you don't want to be too far off. The downside is it's usually also a limit that's enforced by killing the job. So you don't want to, it's kind of like the Price is Right. You don't want to be, well, okay, the Price is Right was if you're over, right? Was it? Anyway, you don't want to be on the wrong side of wall time. Your job's going to get killed when you hit this limit. So it is very much like the Price is Right. But accuracy really makes stuff. And so you want to be as accurate as possible, but not under. Or sorry, not over. No, not under. Not under, because you're going to get killed. Sorry. I said the Price is Right, and then I got a mess. Also, so far, workload management systems have a design space. Like any complex piece of software or hardware or anything that's been designed, there's a design space in which they work well. And I'm talking about every single one, sort of workload management systems in high-performance computing. The design space is sort of set up for jobs that run kind of around, a minute to an hour, but, longer is okay, and shorter to some extent is okay, but I'll say 10 seconds to a million seconds. So a million seconds is about a week and a half. The problem is if you run for more than a week and a half, something's going to happen. The administrator's going to come in and change something. A node's going to go down in a way that it's not going to, and the likelihood that something goes wrong with your job is high enough that I don't recommend going over sort of a week and a half. By the way, systems don't require you to enter seconds. It was just my editorialize, and when I figured out that 1 million seconds was about a week and a half. So, on the other side, with 10 seconds, there's a certain amount of overhead to doing some of this extra work. And that overhead is going down and down, and I know that I was going to put 1 second, because I know we can handle 1 second jobs pretty well, but the design space is really pushing its way up a little bit higher than that. So if you find yourself saying, oh, this is great, I have a solver and it's going to solve this, I'm going to add 2 numbers and I'm going to make that a job, probably not the best use of workload management. You want to do something that it takes, a few seconds to actually compute, 10 seconds, a minute, on that order is much better. Actually, typically, we're talking about hours. So I'll just say that the usual space is sort of 1 to 8 hours is a usual kind of thing what people do HPC. But outside the space of 10 seconds to 1 million seconds, you're in trouble. The second thing, and this is a little bit harder, but there is a way around it, is that since the software is configured really heavily at every single site, you can't hard code stuff into the application. And so this is sort of annoying. There's an easy out, which I put at the bottom, but it's annoying, but you have to do it. So you can't hard code in, oh, well, great. I know my application runs best on 8 cores as a whatever using Intel MPI, so I'll just hard code that in and I'll compile it in and I'll ship my application, it'll work. It's not going to work. And it's not going to work because that wouldn't be an acceptable solution. It's not going to work because everybody configures things differently. And the majority of stuff, actually, that you need to package around your job is stuff that the site's made up. Right? So there's no standard in defining, what names mean what. So, and in fact, even to the point of n mics, which I'm using here to represent 1 Xeon Phi, it could have been n mic without the S. So the ability to actually let the site, after they've installed the software, still be involved in the configuration of how the solvers run is really important. So when you're combining, and when you're taking an HPC application and you're converting it to run in this solver mode and batch mode, you want sort of a translation layer that is configurable at the site layer. So you really want some way of sort of site modifiable scripting. And that doesn't have to be, I've shown everything in sort of shell scripts here. It doesn't have to be shell scripts. There's also good technology. We have actually a neat plugin that would let you do this too. That's not shell scripting. That's even easier. But at least shell scripting is what you want to think of. You don't want to think of, well, I'll just link directly with the APIs and I'll hard code in these keywords and everything will be fine. It won't be fine. And then finally, data. And this is the last of the 3 sort of bits of advice. And I didn't say much about data for 2 reasons. So one reason is if you're just getting started, chances are you're going from a workstation and sort of onto a smaller cluster, maybe in-house. Chances are the file systems are just cross-mounted and you don't have to worry about data at all. Whatever data is on the workstation is going to be in the same place on the cluster. And in fact, if you were in this room 2 hours ago, 2.5 hours ago, talking about OpenHPC, you can see the very first release of the OpenHPC stack that was talked about here was targeted at, okay, there's going to be a shared file system. And there's a reason for that, because in the small spaces, there is a shared file system. It makes everything easy. So maybe you don't have to worry about this at all. If you do have to worry about it, you actually have to get yourself into sort of, okay, that means I have to stage in and out. I have to move files. In workload management parlance, that's called staging. Move files in and out. There's directives to do that. Just be aware, be aware that, okay, if you're actually going into a cloud, chances are the enterprise did not mount, the Lustre cross cloud into local, and so there will be some staging that you actually have to deal with. Data is also really big, so you might think about sort of pushing some users off to remote visualization. There's some really great tools. Plug for Altair, come see us at the exhibit hall tomorrow or Tuesday or Wednesday or Thursday. You can see our remote visualization solution. One more thing is just beware of NFS. So small folks, probably not a problem. If you've got 20 nodes or something, you can deal with NFS, it's okay. But once you're running, say, a 100-way, 1,000-way MPI job, and if the site has decided, the home directory, NFS is fine, we'll just mount that with NFS, don't worry about it, just grab your input files, dump your output files to NFS. chances are NFS is going to break with a 1,000-way MPI job if everybody's trying to read and write to it at the same time. Forget about just everybody like on the entire system, just in your job, your 1,000-way job, it's not going to work. And so in cases like that, you're going to have to go, oh, you're going to have an option. So again, as an HPC writer, you don't know what's going to be there. So if there might, at the very least, you need an option to sort of tell people, oh, here's how you can retarget your input file. We're not going to always assume it's in your home directory. We're going to let you put it somewhere else so that if home directories are NFS mounted and we want to run 1,000-way, we can do that by retargeting where the input and the output goes. So you don't want to do that. And that's that's actually all I had. The future, I was going to say a bunch about the future, but I've given up predicting correctly the future. I really hope that we're actually going to see some better user experiences in the future by taking some of these applications that are running really on just workstations right now and making them run much faster. I have a little bit of time for questions. I can also show you a demo which doesn't have almost any HPC in it, and that was the point of the demo, which since I have 7 minutes, I'm going to do it. I wasn't sure I'd have time for the demo. By the way, we have a BOF on Wednesday at 5:30. Want to know more about our stuff? Because I'm not really marketing it here. Come to the BOF. Let me just show you what this might look like. So if you are a developer of an HPC app, say on Windows, and again, I'm shamelessly stealing from our own pool of applications. I'm using Inspire. So here you would launch your application. This is how you normally do a launch of an application. You would go grab, by the way, no workload management interface yet, nothing. This is just the application. We're going to build something. We're loading a model into Inspire. Okay, it's not a very interesting model, but it has some forces coming down from below and up from below and down from above. Now we're going to actually just say, hey, I'd like to do a quick optimization on this. Let me choose a machine that's not local. So that was it. We would choose a machine that's not local, and here it says, okay, please run that. You can't see this from here, but that says run. And that was the entire, that's what I hope to eventually have all applications when they're linked up with workload managers, is those like 7 frames that you saw. Choose that I want to run remote, push run. We're now watching it. It actually, you saw the little green bar come over. It just finished. That's the entire interface between the workload manager and this application. And that's all done, again, inside of here through scripting. Double click, poof, and it pulls up the rendered version. And so if this was a way more this is actually not very complicated. You could have done it on your workstation. If this was a hugely more complicated model, you could have gone from something that, say, takes 5 hours on your workstation, something you have to wait till nighttime and say go and run and then come back the next day, to something that you could push a button and run out in your cloud or on your cluster in 5 minutes, and you'd have the exact same experience, but okay, I'm designing an entire bridge instead of what is a cube here. So that's what I want for the future of workload management. I want nobody to see it on the user space. All right, I'll stop there and find out if there's any questions. Thank you. Yes.
Job manager. Do you see that as something that's just reading registers on all the nodes before and after the job runs, or do you see that as something that would be an active daemon on the process, not on the nodes?
Okay. So the question was about power management and whether it's sort of read the registers before and after, find out how much power, or do some summary at the end, or have an actual active read the power all the time. Both. I mean, so here's the thing about power, right? Power, like most things, is not something, like network bandwidth, for example, or even like CPU usage. Is you can get an aggregate at the end, and you can get a single number. Actually, you can nicely get a single number. So power use, you have to measure instantaneously, right? Because power is exactly what are, how much pressure is there now. Energy, on the other hand, is kind of is the integration of power over time. And so I guess I'm most interested in and I think the big win initially is going to come from actually energy accounting. So I should have said energy accounting, not power accounting. I'm still getting myself used to that. But I think the same way that you want to tune your job for MPI in terms of latency and bandwidth and message sizes and where your collective operations are and your barriers are, and so you'll go in and you'll look at how the network is being used second by second. You may want to do the same thing for power, and once you not energy but power, and once you do that, you're going to actually want to get a stream with effectively some way of reading power second by second all the way across the machine. By the way, if you want to actually do power capping, you have to read it all the time, because if you're going to cap your system to 0.5 megawatt so that the chillers don't melt or whatever it is, actually it's probably the PDUs don't melt, the chillers, PDUs don't melt, you're going to want to know what the power is all the time, although I suspect that you'll just have a circuit breaker for that just in case you miss. So the interface between PBS Pro and the power management stuff that we've done, we are depending on other people to build the daemons that actually measure the power and report it back to us. And so we're working both with Cray and SGI, who are building in power management, and we're actually working with others. We just haven't released stuff yet on power management. And our view is the hardware should kind of do the best job it can of the measurement of the power, and then we're going to use that for the scheduling part and the reporting part. So will we do one totally on our own? I don't know. Maybe. I mean, right now, those guys are doing a better job than we could do because we don't know the hardware, and I don't want to have to, if you've looked at power on the board, there's a board, and it's got the power supply, and it's got this chip, and this and that, and I don't want to have to figure out for everybody's board how to sum that all up. And if there was an interface, we would do it. In terms of how we're doing it, we're interfacing PBS Pro with these systems that read power, through an abstraction layer, using the plugin framework that we have, so it's easily replaceable. So if some new person comes along, or you build your own machine and you want to actually plug something in, there's whatever, I'm going to make the number up, but there's 12 calls. You just put those in, and poof, we can connect the two together. Other questions? Okay. Thank you very much.